Hi, in this video, we want to introduce moving average models for time series. All right, so our idea is that what we're going to do is that we are going to, in a regression type manner, we are going to assume that we have another time series of Gaussian random variables, which are white noise, and we're going to take a linear combination or possibly an average of those, and that is going to manifest the time series that we actually see that we're interested in modeling. All right, well, before we get into that, let's go ahead and give credit where credit is due. We're going to be taking some examples from time series analysis and applications. Here are the authors' names. Here is the GitHub page and information about the R package that they built up. It's a very good package. And UCF students can download the textbook for free through UCF's library. All right, so now let's get into what we are here to do. Okay, so previously we looked at autoregressive models. In autoregressive models, the idea is that we're going to have regression on previous observations to predict future observations. Well, here we're going to, in a sense, we're going to have regression on some Gaussian random variables that I don't actually see. And we're going to have coefficients times previous values of the Gaussian time series and the Gaussian random variable for the current state added together to be what equals the time series I'm looking at. So we have autoregressive, where we're putting coefficients times past observations. Moving average, what we're doing, we're taking coefficients times Gaussian random variable white noise time series. And down the road, what we're going to do in the next video, we're going to combine those into autoregressive moving average models. And then we're going to kick it up a notch even more after that into autoregressive integrated moving average models. All right. So for a moving average model, what we're going to do is that we're going to say that the time series that we are looking at, the actual value we have, is this particular linear combination of some white noise time series. So here is the current value of that white noise time series. Here is 1 moment ago. Here is 2 moments ago, 3 moments ago. And we're going to say we're going to go back Q lags. All right. So then we're going to have these coefficients that we multiply by the past values. And these coefficients are constant parameters. And we're going to assume that that Gaussian white noise is white noise with mean 0 and constant variance. And in this formula, we're going to assume that this coefficient here is not equal to 0. So when I say Q, that is indicating the largest shift back of all the coefficients. Now, some textbooks will have negative values times those, or negative numbers in front of the coefficients. Instead of having a plus, they'll have a minus. So if you see this, it's just a different buildup. It will make sense for what you're doing. The mathematics will take a little bit of tweaking, but not much. Now, one thing that you need to do before running this type of code, this type of model, if I'm in R or SAS or Stata or whatever SPSS, I need to check with the help documentation to tell me how to interpret these coefficients. Is the formula with a plus sign or a minus sign? If I don't look at the help documentation, I don't know how to interpret it correctly. All right, so now we can take a look at this model with a backshift operator. All right, so here in this notation, what we're doing is that we're saying our time series is equal to some coefficients. So this is an operator on the backshift operator, cumulatively another operator working on the white noise term, the time series that is. And so what's happening here is that this function, the theta, is defining a function using these coefficients that looks very similar to a polynomial. It's not a polynomial, it looks like one, especially how we write the backshift operator with superscript. And what we're going to do, we're going to make a bridge between this notation and polynomials, and we're going to analyze those in a future video. And so here, this is just to get us comfortable looking at the backshift operator aspect. So it's important to understand that what's going on here is that I have two functions. I have the first function is this theta, and that is this function, well, the coefficients. And I'm going to have the backshift, like this would be backshift of 3 corresponding, backshift of 2 corresponding. So the theta is operating on an operator itself, and then that gives me an operator to drop the time series into. So we're invoking a little bit of abstract algebra here for this. All right, so to write that, here is the moving average operator on the backshift operator. All right, so when I look at this, something that the author does differently than what I do is that they put a 1 here for the backshift operator of no shifting. That is the identity operator. That makes sense if you're comfortable with college algebra. I like to explicitly put a 0 there. Now, these superscripts are not exponents. These are iterations of the operator. So this one here, this indicates that we shift back on the time series 2 time steps. We shift back on the time series 1 time step. Here we don't shift at all. And here we shift backwards on the time series q times. All right, so now let's take a look at an MA1 process. So we're going to take the formula we just looked at up here, and we're going to stop at just one lag term in our white noise time series. And so this is our model for this example. And what we're going to do, since this is an introduction, we're going to go pretty deep into this model to give us a full understanding of what's going on. And the goal with this is to give us a better understanding of what's going on for moving average models in general, also to get us comfortable with the tools that we use to analyze time series. We're going to work on moving average 1 before we work on moving average 2, moving average 3, and so on. We're doing baby steps, training wheels, we're walking it in. All right, so if this is what I've got, you notice I've got white noise terms, 2 of them, and I've got a constant. So if I take the expected value, well, that's going to be expected value of that white noise term, expected value of this times the theta. Well, that's just going to be 0. Boom, we've got our expected value. Now, when it comes to covariance, well, white noise is always independent of all other white noise terms. So the only way I have a non-zero term for my covariance is when the indices match up. And so when I look at covariance and I have a shift of 0, of course, that's going to be the variance. And if I just sit down and crunch it out, I see that I'm going to have 1 plus theta squared times the variance of the white noise terms. Okay, now if I shift 1 over, if I do a shift on this, let's say I look at t with t minus 1 here, and then I shift, then this one becomes, when I do the shift, this becomes a t minus 1. When I do a shift, that becomes a t minus 2. All right, well, the t minus 2 isn't going to match up with anything, and this will be a t minus 1. It will match this subscript from the original. And I sit down, I crunch it out, I say I'm going to get theta times the variance. And then for any larger shift, there's no overlapping indices, therefore the covariance is going to be equal to 0. Now, to go through and compute the correlation, I take the covariance, I divide by the variance, with a covariance with a shift of 0. And of course, we get a variance of 1, or a correlation of 1, I misspoke. And then we have this fraction here. And this will be with a shift of 1. This is our correlation between consecutive observations. And there's going to be 0 correlation between all other observations of our time series. Now, if I take a good hard look at this correlation, I can see that that has an upper bound of 1/2. And that will be achieved when theta is equal to plus or minus 1. So the maximum correlation between any 2 consecutive observations in an MA1 model is going to be the maximum correlation is 1/2, and that will be achieved when theta is equal to plus or minus 1. Now, something that's very interesting about this is that if I was to replace this theta with 1 over theta, like I do here, notice what I've got here. I took this fraction, and instead of theta, every time I see a theta, I replace it with 1 over theta. If I sit down and crunch that out using college algebra, what we'll see is that I get exactly the same fraction as I have up here. Okay, so this means that if I have theta or 1 over theta, I'm going to get the same correlation. Okay, well, if I can get the same correlation, is it possible for me to get the same, if I modify the theta, I get the same correlation. If I modify the variance, is it possible for me to get the same covariance? Yes, it is. And it's going to work out that what we can do is I can choose my variance, I can choose my theta to get stochastically the same random variables. They're stochastically equal to each other, even though they have different parameters. So we have a non-uniqueness. Why is this important to us? Because if I see the data, what I can do, I can pick the model that has the features that I like in particular. Specifically, I want the feature of having theta being less than 1 in magnitude. All right, so something to point out is that moving average models of shift 1 have 0 correlation for 2 or greater shifts, while autoregressive 1 models never have 0 correlation between their observations, even if it gets really small. All right, so now let's take a look at 2 moving average models with just 1 shift. We'll set theta to 0.9 and to negative 0.9, and let's look at the difference. Here's my code for doing a simulation. So I'm using the ARIMA.sim function. Here I'm setting, I just want 1 coefficient for the moving average model. I want to generate 100 observations. So this does the simulation for me. And the TS plot function from ASTSA package gives us the visualization. And boom, we've got it. Okay, so we can look at that. Now let's contrast this with what we get when I change the coefficient to a negative. So it's the same magnitude, but negative. Now notice that this is a lot more up and down, up and down, up and down because of that negative in there. So that we're going to have a negative correlation off of that correlation formula that we looked at a moment ago. And so it's a lot more choppy, while this one is going to look smoother. All right, so let's go ahead and dig deeper into that non-uniqueness aspect that I talked about a moment ago. All right, so if I take an MA1 model, let's say that we're going to take 2 models and they're going to be stochastically the same, that is, they're going to have the same distribution for their observations. First one, we're going to say that the variance of the white noise is going to be equal to 1. All right, there's a typo here. That should be a 1. This should be a 25. But all right, that's okay. We'll keep on rocking it. So pretend that there's a 1 there. Pretend a 25 is there. All right. So now here, if I have a variance of 1, theta of 5. That should be. Oh, this should be 1 over 5. Oh, I did mess this up. If I have this time series and I have this time series, then it's going to work out that we're going to have stochastically the same every single time. And so what will end up happening is that if I crunch out the correlation and the covariance, I'll have exactly the same for both of these models. Now, I have two models. So like, let's say I was looking at some data and I have to pick a theta, I have to pick a variance to model what's going on of this. I want to find the best fit. Well, I'm going to get the same output from a fit point of view on either one. So I'm going to pick the one that gives me the model features that I like the most. Specifically, I'm going to say theta is less than 1 in magnitude. And when I do that, what's going to end up happening is that my summations, as I take it to the limit, are going to converge, and which means I'm going to have a better, more complete model for what's going on. All right, so what I would do if I had data, I had those two competing models, I would pick the one with variance equal to 25. Theta is 1 over 5. Here is the iterative formula, like that. And here, this is my formula using my white noise terms. All right, so now we want to just take a look at what we're going to be doing when we talk about analyzing moving average models using series and polynomials. All right, so here we're using that backshift operator notation we talked about a moment ago. Here I'm writing my current model that I'm interested in. Remember, I had the theta. So here I've got 0 backshift, and I have a backshift of 1. Well, I can rewrite, let's go ahead and write this out as pi of backshift operating on x of t is equal to our the white noise term. And so you'll see that I've got WT here, I have WT by itself. And so when I use this operator on X, I get W. When I use this operator on W, I get X. Now, if everything is the way I would like it to be, what's going to end up happening is that we have a, if we have invertibility, then it's going to end up that this pi operator is equal to the inverse of theta. Now, this is not 1 over theta. This is the inverse operation of theta. And so when I talk about inverses, there are specific cases that we're going to dig into the most. If this is my polynomial representation, my characteristic polynomial for the time series, then its inverse is going to be this rational function. Well, what I'm going to do, I'm going to convert this to its time series, excuse me, its power series representation. And then that gives me the power series representation of this pi operator. And so this gives me a tool to analyze the inverse of the original operator. And so this gives me a way of going back and forth between X and W. All right, well, that's all I've got for you. Take care and goodbye.